Good morning, everyone. Today is Friday, March 29th, 2019. Thank you all for um, joining me this morning. Today, the focus of the discussion is going to be an upcoming nor'easter for Wednesday. This storm is really interesting because here is what I'm trying to show you guys. Right here, look at this. Boom. Big storm. But here's the thing. You have basically the inclination of a positive PNA, a ridge on the west coast, right here. See a ridge, and a trough on the east. An inclination of, a positive PNA, warming in, Alaska. This is not a highly positive PNA. This is slightly above like neutral. However, look at this right here. You're having a trough on the east coast, storm developing here, and the storm is now pulling northeast. Depends on how sharp the cold air will be. Will it be all the way down to the coast, or will it be further west? Um, One thing the GFS has trouble with, it has trouble with dynamic cooling. I've noticed this model does have that issue. The best model for the dynamic cooling is the NAM, the short resolution models like like the RAP, the NAM, the Nest are really good with dynamic cooling. However, it is not good with the GFS. I mean, as you can tell, this model really underplays the effects of dynamic and evaporational cooling. So that's one problem the GFS has that it needs to correct. Um, Beside that, it handles precipitation rather well, except the part of dynamic cooling. Um, I mean, it's not a short resolution model, so obviously it's not going to handle, you know, short resolution stuff very well. So, as I said, this is the precipitation outlook. This is how much rain will fall from this event. This is so this is a weather event that's going to come through this weekend, especially Saturday and into Sunday. Sunday, it's going to just be a little bit of precip for New York. But some of the heaviest precip will actually be upstate New York, Ohio, through northern Vermont and into Quebec. So Quebec City looks like it's going to get quite a thumping of rain and snow. So it looks like some good amount of snow is possible for Quebec City. And right here, boom, just check that out. I mean, if there's enough dynamic cooling, this could be quite a bit of snow. If the GFS is actually accurate and the dynamic cooling will be less than expected, it's going to be all rain. So let's look at the GEFS. Okay, let's look at mean precip accumulation. Mean precip accumulation here. So see, the the GFS is hinting at a pretty big storm. Let's look at mean temperatures. Yeah, it looks like the snow threat is not going to be that extreme because usually the GEFS does handle dynamic cooling a little bit better. So yeah, looks like not a big snow threat. Um, so looking at the Canadian again, I just want to take a look at the Canadian. I just want to reanalyze it. Okay, finally loaded. Let's take a look. Yeah, this model is not handling it very well. Let's look at the ensemble for the European. The European ensembles are hinting that this storm might be more intense than the other ensembles did. So we're going to take a look at some volcanic activity after we look at the models. I want to point out some interesting volcanic activity right now in Indonesia. And last night I made a video about Popocatépetl having that major eruption that occurred 2 nights ago, or I believe 2 to 3 nights ago. So it kind of hints that it might stall in this area. You're going to have a storm that's going to kind of try to race up the coast and then basically stall because of this blocking high. When you have a blocking high, highs do often keep the cold air in, but sometimes the storm can override the cold air, and the cold air can dissipate if the high lingers and become, the weather can become hot under a high pressure system. It's only when the high starts coming in it brings in cold air, because a high is sinking air while a low is rising air. Sometimes if a high lingers on one area for too long in the summer, it gets very hot. While a high pressure system does bring in cold air initially, if it stays in one area too long, temperatures get really hot, and then the high can sometimes linger, or sometimes the heat itself can cause the air to rise and an area of low pressure can form. Like sometimes you get desert lows that can cause the monsoon to form, because you get moisture from the Baja California, from the Pacific, from the Gulf. Because these desert lows from all the heat can sometimes form their own thunderstorms, those monsoon storms. You're getting moisture from these surrounding bodies of water. So let's look at thermodynamics, 850 millibar temps aloft. So this is hinting that temperatures will be above freezing at 850 millibars. So looks to be mostly rain. Oh yeah, I'm pretty exhausted right now. So let's take a look at the NavGem. I think it's still going to be only showing an 18Z run. Yeah, this run doesn't do that good. So it looks less and less likely that there's going to be a snow event. The storm looks more and more likely, but the snow event is looking less and less likely now. Yeah, NavGem is not handling this very well either. I think the best model that's handling this at the moment is actually the GFS itself and the European. I think these are both handling the storm pretty well. The JMA is also handling it pretty well. I think these three models, the European, the GFS, and the Japanese Meteorological Agency models, handling it pretty well as well. These are the three, I call these three models the three kings of model forecasting. I mean, sometimes these models can do very well, especially if it's less than 100, like 100 hours out. These tend to perform very well as well. So does the NAM when it's less than 60 hours out. So a lot can still change, but long range, these three models basically do the best. Because, I mean, that's what their job is. They're long range models that go at least a week out. This is a week. This is up to 2 weeks out. So for less like 5 to 7 days out, this is probably the most accurate model. While the European is, I would say, the second most accurate. And the GMA is the third most accurate. Sometimes these models can get it right as well. This model can get it right too, but it's pretty rare that this model can get it right, so far out. Usually for that, it's usually this model, and this model here, in order. In fact, you could also compare model runs too. For example, you could also compare the model runs up to about a week out. So let's for example use the GFS, right? Let's compare, this is right now what it's showing. Why this model of saying is going to be less cold air is because you see how elongated the storm is. This elongation will try to force the colder air further west. If you're going to have more of a concentrated low, just a more circular, with the precipitation still being further, just as far out, the cold air will be more concentrated and more closer to the coast, and maybe even going even a bit offshore. This is why it's going to, basically, the low will be more elongated, which will allow a more warm air fetch towards the west. So let's look at the 12Z run. Because the 12Z run of the GFS was showing more snow for New York City and for southern New England. There's going to be a difference. There's going to be a key difference. It's not only elongated, like, no, you see, it's more circular. You're having a more wound up system. Not only is it closer, but it's more wound up. So let's look at frozen. So because it's more concentrated, the air aloft will be colder. So this can still happen. That is also a likely scenario too. So you see how the cold air is hugging the coast, while here, the current run, look what it's showing. So just, this is the position of the low, right? It's just about here. See, it's taking its time. So it is further west, but the thing is, so see, it's stronger and there's more cold air with it. So let's look at snowfall, total snowfall accumulation. So you see, it's also hinting at snow for New York City too. While this run, the current run, and let's look at the difference between the previous run, the 12Z, and the current run. Just let's look at the difference. You're going to see almost no snow. Look at the snow. You see big snows here, and then nothing. I mean, just look at this. You see how ridiculous this is? You're going to have a lot of snow in North Carolina, up to about like 6-7 inches in northwest South Carolina, and all of a sudden, no snow, and then it snows again once it gets to Canada. Doesn't make a lot of sense, if you ask me. This model, though, makes a lot more sense. So less snow, then more gradual. This is actually a lot more likely, if you ask me. I mean, you still have at least 6-7 days out, so, well, not 7, but you have at least, like 5 days out until that happens. So with 5 days, with still 5 days to go, a lot can still change, and the storm could still change. It's a very dynamic situation, very changeable. So this is looking at Indonesia, Magma Indonesia, the seismogram station. So this is because, right here, this is because of mining activities. Pumice mining, Agung and the Batur, both Agung Batur volcanoes are very explosive. They produce high quantities of pumice, and pumice is even used in soap. I don't know if you've ever used pumice soap. It's really good for washing your hands. Pumice is basically this lightweight material because it floats on water because it's so full of air. It's a very airy magma. It's basically magma that was blown out of the volcano, and it solidified as it was thrown thousands of feet, tens of thousands of feet into the air, and it solidifies into rock. But because that rock is so light, it floats on water. Like it's basically like rock foam, basically. And it's created because of air bubbles that are trapped in magma. And it's the same reason the volcanoes are so explosive. It's all that air in the magma. The more air trapped in the magma, the more explosive the volcano is. Basalt, on the other hand, is heavier than water, and it's going to sink because it is more dense. It has less, you know, gas in it, so it's more fluid. It flows. Um, the Etna volcano, it's kind of a mix. It has characteristics of a shield volcano and a stratovolcano because it is a subduction zone volcano. It is not a hotspot volcano like some people believe. However, Etna was a shield volcano. However, it is a subduction was a subduction shield volcano. There are several volcanoes in Vanuatu that are shield that are subduction zone created. Like like Ambre Island is a shield volcano that is created by a subduction zone. And because it is created by subduction, it is more likely to turn into a stratovolcano. Shield volcanoes are typically formed by hotspots. You can also have stratovolcanoes and explosive eruptions from hotspots as well. Take, for example, Yellowstone and some of the Icelandic volcanoes. But Iceland is more dynamic. It's a combination of a hotspot and also a rift. And also you do have basalt, I mean, also rhyolite in Iceland because there's also rocks that are, you know, there's some um, silica there, and the silica is what makes the volcano more gaseous because the silica causes the gases to bind to the magma. That is why um, the more silica in the magma, the stickier it gets. Volcanoes that has the least silica are considered basalt because the gases escape easier. All volcanoes have silica, but the volcanoes with the least silica are basalt. Then the next level of after basalt, you have there's like stages between basalt and andesite, but you jump a few stages, it increases of silica, then you get to andesite. I mean, also you could there's like hybrid between like andesite and shield. I mean, and basalt. Those are more dynamic. Those are more like Etna and Vesuvius, because Vesuvius is a composite volcano. It does sometimes have lava flows too, but predominantly explosive eruptions. Etna predominantly effusive eruptions, but you could also have pyroclastic flows from the magmatic eruptions too. There was this crater that had a. I'm actually going to show you a video right here. Etna. Well, my bad. Etna. Yeah, right here. Etna pyroclastic flow right here. This is the video I want to show you. This is the crater of the volcano itself. So keep in mind, these are not because of interactions with water like some people are led to believe. This is a magmatic, purely magmatic eruption. This is a stratovolcano that has, see, you can see the magma right there, right? Yeah, you clearly see the magma erupting. So these are not phreatic eruptions at all. These are magma-driven eruptions. In some cases, yes, some of the explosive eruptions at Etna are driven by interactions with water and magma. But these are more magmatic driven because you can see the magma coming out of, oh, the lava coming out. I mean, look at this. Just check this out. So this is definitely a stratovolcano. It's behaving more and more like a stratovolcano, though it also demonstrates shield-like characteristics when it has flows. Why is this happening? Because, as I said, Etna is a subduction zone volcano, and now the magma is changing composition. It's becoming more and more stickier. However, not all of the volcano is sticky. Some of the some of the volcanoes also has less silica and it's also basaltic. So you have a basaltic, magma, and you have also silica-based magma, which is more eruption, more explosive. So a silica-based, more explosive magma type, and a less explosive, more basaltic-based. Mount Etna lava flow. So this here is a demonstration of what happens when you have a basaltic-based eruption.
Saving the environment isn't always easy, but there is one thing you can do every day.
So you see, this is basaltic. This is basalt right here. Just like in Hawaii. This is pure basalt, just running down. And this is just like in Hawaii. Though it's not formed the same way. Hawaii is formed by hotspot. This is formed by process of subduction. That's the difference between Etna and Hawaii. Etna is caused by the subduction of the African plate beneath the European plate. That's why Etna's, has a split personality. It demonstrates both types. Also, Etna emerged from the ocean in the last 500,000 years, so it's a relatively new volcano. But the older it's going to get, the more explosive it's going to get. Because older stratovolcanoes tend to be more explosive, while new volcanoes that just emerge out of the ocean, stratovolcanoes, tend to be more effusive. But not all. Because if the volcano is going to be underwater for a long period of time, it can also be more explosive. Like there was an eruption from an underwater volcano that erupted a huge amount of pumice. That meant it was a more stickier magma. Subductions, yeah. So I'm just going to show you. Yeah. See, usually, it's not always. That's what they say. Usually. Keyword is usually. You can also have stratovolcanoes at hotspots too. If water somehow gets into the vent. 90% of the volcano is lava rather than pyroclastic material. It's a large basaltic shield volcano. It's an arc. And how does that arc form? So it's a shield volcano. Let's see. So, is it a hotspot volcano? It confirms with the tectonic pattern. This is a subduction zone. It's obvious it's a subduction zone. It's caused by the subduction of the Australian plate beneath the Pacific plate. See? Trench volcanic chain. That means it's subduction. The trench is where the oceanic plate dives beneath the continental oceanic plate dives beneath the continental plate. Why does this happen? Continental plates are less dense, actually. You would think that a continental plate is more dense. No, it's actually not. Because of the weight of the water above, the oceanic plate is actually heavier than the continental plate. And so therefore, the oceanic plate dives beneath the continental plate to a depth of 2 to 500 kilometers. And here's a funny thing: the water in the rocks actually lowers the melting point of the rock. Actually, an interesting fact I recently found out. Just past year, I found that out. Lowers. Yep. Boom. Isn't that cool? This is because of, chemical reactions. So let's look again at the model of the European. Because actually now it's getting closer to 2, so I'm going to probably end the video now. Thank you all for watching and have a great day. And if you want more interesting content, more science information, weather information, please subscribe to my channel and like my videos and hit the notification bell. Because beside weather, I will be talking about volcanoes, earthquakes, and just let's check one more look at the earthquakes around the world. So, pretty healthy swarm in Yellowstone. There was a 2.0, 14 kilometers worth of Old Faithful, 8.3 kilometers, magma chamber depth. This one here, that's a little more shallow, so it's probably related. It's probably the depth might be wrong, but majority of the volcanoes are pretty deep. So 8.3 kilometers, 4.8, 8.9. So this one is 10 kilometers deep. But this is definitely a swarm. So as you can see here, there is a swarm going on. But so here's so they're all at different depths. So this could be tectonic in nature. This could be the main shock. And these could be aftershocks. However, let's just take a quick look before I end the video. If there's been any stronger events in the past 7 days. Nope, none. So this is most likely just small rapid fire swarm. Let's look at the time. All within 16. So here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All within this area here. So this area is very seismically active. And then look, another rapid fire swarm here. So there was 1, 2, 3, 4, 5, 6, all within the same hour. And this is the one outlier here. But beside that, you had 2 rapid fire events here. 1, 2, 3, 4, 5, 6. Save for this one, and then 1, 2, 3, 4, 5, 6. And all of these events were greater, at least 3 kilometers in depth, while this outlier one, 2.1 kilometers depth, most likely hydrothermal. Magmatic, hydrothermal. Anything below 4 kilometers is most likely hydrothermal in nature, but it could be magmatic too. So it's just so I'm gonna end the video here, and tomorrow I will do a seismogram update. Actually, okay, I'm just gonna take a quick look. Well, thank you so much for watching, and just wanna thank you all again, and just let's take a quick look here. Yeah. Oh. Look at that. That's a weird event here. Very strange event here. So earthquake. I don't know what that was here, but probably related to hydrothermal activity. This is magmatic hydrothermal. And yeah, this it's not picking up on this. Here are the earthquakes that all the other stations picked up. Definitely looks like a VT earthquake. Well, thank you so much and good night.